Hey folks, my name is Nathan Johnston, and welcome to Lecture 21 of Advanced Linear Algebra. The idea behind today's class is to think back to early in the course. We introduced abstract vector spaces, and we showed that we could do all sorts of neat linear algebra things in them, but in a sense they aren't actually that much different than Rn, because what you can do is you can take your abstract vector space and just represent its members via coordinate vectors, which are just lists of n numbers. Well, what we're going to do in this class is we're going to do something similar for inner products. We're going to show that, yes, inner products, they're more general than the dot product, but in a sense, they're kind of not as well, because what you can do, well, for any inner product on a finite dimensional vector space, you can make it look like the dot product just by choosing the basis of your vector space appropriately. And this is where orthonormal bases are going to come into play. We're going to see that you have to choose your basis to be orthonormal for this to be true. Okay, so let's dive right in. Let's see how this works. And we actually don't need any sort of mathematical preliminaries to get to this. We can dive right into the main theorem of the lecture. And here it is, okay? The theorem says all inner products, they look like the dot product as long as you're looking in a certain basis, all right? So suppose that you've got some orthonormal basis of a finite dimensional inner product space V. Okay, so this is really important. The statement of the theorem is not true if you forget about this word orthonormal here, and we'll see in the proof where that comes from. Okay, so great, you got some orthonormal basis of a finite dimensional inner product space. Then what the theorem says is that, well, then the inner product on that inner product space is just equal to the dot product of the coordinate vectors of the individual vectors in that vector space, right? So you can think of the inner product really as the dot product as long as you look at things in the right basis. All right, so where's this come from? The way to show this is, let's start off, let's give names to the members of that basis B. And now, because B is a basis of that vector space, of that inner product space, you can write both V and W as linear combinations of those basis vectors, okay? So that's all we're doing there, okay? And we've given C's are the names of the coefficients in the linear combination for V, and D's are the names of the coefficients for the linear combination for W, okay? And now what we're going to do is we're just going to compute this inner product here. We're going to compute inner product of V with W, okay? And after we simplify, we'll see we get exactly what we want. So how's it work? Inner product of V with W, well, just plug in these linear combinations that we had here for V and W, okay? And I'm just switching to summation notation here because we're going to have sums all over the place. It's just going to be much more compact and easier to read. All right, now the first thing that we're going to do is we're going to use sesquilinearity of the inner product, okay? So in other words, I'm going to use the fact that inner products, they're linear in their second entry and conjugate linear in their first entry. So what I can do is I can pull this linear combination out of the second entry in the inner product, and I can pull this linear combination out of the first entry in the inner product, as long as I remember that the inner product, it's only conjugate linear in the first entry, not linear, okay? So I need to throw complex conjugates over those CI coefficients there because it's only conjugate linear in that first entry. All right, now the next thing that I'm going to do is I'm going to look at these terms here. I'm going to say, oh, well, those are inner products of things from an orthonormal basis. So in particular, because an orthonormal basis is mutually orthogonal, whenever I does not equal j, here I've got an inner product of two different members of an orthogonal basis. So that inner product is going to equal 0. So what happens is whenever these two subscripts don't match, whenever I doesn't equal j, this term goes away. It's 0. So I've got this big ugly double sum, except all of the cross terms in this sum just equal 0. They're not actually there. So the double sum collapses down to just a single sum where all of the subscripts match. Okay, so I end up with just this sum here. It's the exact same sum, except now all the j's are i's, and it's only one sum. All right. Next up, I'm going to focus on this term here, okay? Now I've got an inner product of a vector with itself, and that vector comes from an orthonormal basis, okay? So now I'm going to use the normalization condition, right? Remember, every member of my orthonormal basis has norm equal to 1. In other words, the inner product of it with itself equals 1. So this guy here equals 1 because of the normalization condition. So I can just drop it, and I'm left with just this sum here, the sum of the product of the coefficients from the linear combinations. And then this sum down here, well, I just recognize that. What that is that's just the dot product of the vectors C1 up to Cn and D1 up to Dn, right? That's just the usual dot product in the space Cn of complex vectors. Okay, but hey, these two vectors here, these are exactly the coordinate vectors of v and w, right? That's the definition of coordinate vectors. It's the vector that contains the coefficients from these linear combinations as their entries. So that's how we get this, and then we're done. Okay, so that's all there is to it. You just simplify, 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 and then in these last two steps, you just plug in the definition of things that you've seen before. Okay, so yeah, so that's really nice. In arbitrary finite dimensional inner product spaces, inner products look like the dot product. Well, if we specialize a little bit further to say Rn and Cn, then we can say even more, okay? Because remember, Rn and Cn, just like any finite dimensional vector space, they have a whole bunch of different inner products on them, and they can look very different from each other. But in a sense, they don't actually look that different from each other, okay? There's sort of a way to transform between all of them. So let's see how this works. All right. So the idea here is sort of based on change of bases. So our setup is, suppose that we've got E is the standard basis of Cn or Rn, and then B is any old basis of Cn or Rn. Well, if we think back to change of bases and how they work, one nice factor about change of bases is that if I multiply any vector by this change of basis matrix from the standard basis to this other basis b, then I get the coordinate vector of v with respect to that new basis b. Okay, and the reason for this is just that v itself is v with respect to e, right? Every vector is its own coordinate vector with respect to the standard basis. That's sort of the nice defining thing about the standard basis. Okay, and similarly, I mean, the exact same thing happens if you replace all the v's by w's. Okay, so this is true for any v and w in that vector space. Okay, well, if we combine these facts, right, this fact here that we just sort of reminded ourselves of, together with this fact up here that we just proved, then what happens? Well, first thing that happens is that theorem up there tells us that, yeah, okay, the inner product is just the dot product with respect to this new basis. But now, v with respect to b, that's just change of basis matrix times v, so I plug that in there. And then w with respect to b, that's just w times change of basis matrix, so I just plug that in there. Okay, and now remember, one of the nice properties of the dot product is vector dot vector is the same as vector conjugate transpose times vector, right? You can think of it in terms of matrix multiplication. So this dot product here is the same as the conjugate transpose of this vector times this vector. Okay, and if you expand that out, what you get, remember, conjugate transposing a product here reverses the order and applies the conjugate transpose to each of them, so you end up with a v star on the very left, a w on the very right, and then the product of this change of basis matrix with its own conjugate transpose in the middle. Okay, so that's maybe still a little bit ugly. There's still a lot going on there, so it's still a lot to think about, but we can make this even simpler by recalling, I think that actually this is an exercise that we did on an assignment. So every change of basis matrix is invertible. We saw that in the course notes. But the converse is true as well. Every invertible matrix is a change of basis matrix. Okay, so really all that's going on here in the middle is we've got some invertible matrix times its own conjugate transpose. All right, so then when you throw all of this together, we get exactly this corollary down here. All right, and what this does, this theorem, this corollary, it characterizes what inner products on Rn or Cn look like. Okay, so remember Fn, because we've got an inner product here, that field has to be either R or C, the real or complex numbers. All right, so a function, between appropriate spaces, it's an inner product if and only if there exists some invertible matrix such that the inner product has this form here, such that, it looks like the dot product. Remember, the dot product is exactly what you get if you don't have this weird matrix in the middle. The dot product is just v star times w. All right, but every inner product looks like this for some appropriately chosen invertible matrix P. All right, so yeah, if P equals the identity matrix, you get the dot product, right? Because then, hey, this whole thing on the inside is the identity matrix, it goes away. But every other inner product is of that form as well for some appropriately chosen P. So let's go through an example here. Back in lecture 17, we were introduced to this weird inner product, and we showed that it really was an inner product. All right, well, now let's convince ourselves that actually it has this form that we've been talking about, and thus, yeah, it is an inner product. All right, so what we're going to do is I'm going to just sort of tell you the answer. We'll see how we get this answer a little bit later in the course. But the answer is, well, this is the matrix P that we should choose. Okay, we should choose P to be the matrix 1, 2, 0, 1. And that is invertible. Triangular matrix is invertible if and only if its diagonal entries are non-zero. All right, so that is invertible. And let's show that when we plug this matrix into the formula up here, we really do get this weird inner product. All right, so here's how it works. Well, let's start off, let's compute P star P. All right, so this is just matrix multiplication. And what you get is the matrix 1, 2, 2, 5. All right, and now we're going to multiply by V star on the left, W on the right, and we'll see that we get this expression here. All right, so V star times this matrix times W on the right. Remember, you always think about these vectors as column vectors, so V star turns it into a row vector. All right, now let's just do that matrix multiplication, and you can do it in either order. I'm going to do this rightmost product first, and that gives me this column vector here on the right, right? You get 1, 2 times W1, W2, and 2, 5 times W1, W2. So you get that column vector, and now you do the product of this row vector with this column vector, and yeah, you get exactly the expression up here. So that's another way of seeing that it's an inner product, okay? And maybe convinces us a little bit that, yeah, every inner product can maybe be written in this form here. I mean, we already sort of went through the proof, but it's nice to see an example as well. All right, so that's one of the nice applications of orthonormal bases of vector spaces. They let us show that all inner products, well, really, they do just look like the dot product, just sort of squidged around a little bit, just sort of distorted maybe. All right, so that'll do it for today. Next class, we're finally going to answer the question of how do you actually construct construct orthonormal bases in the first place, though. All right, so I'll see you then.